Hey everyone. Again, my name's Adam Benedict. I'm with Power Engineers, and I'm doing the second presentation on DC Schematics. So, I guess in the line of what we're looking at, typically you develop the one lines and the three lines, and we'll talk about that next time. And we're in the DC schematic phase. So we're really trying to set up all our drawings for wiring and programming. DC schematics. And in particular, we're looking at how this relates to relaying. So DC schematics really focuses in on relay indication, breaker failure, transfer trips, annunciators, alarms, test and isolation points, as well as AC and DC station service. So what is a relay DC schematic? And this is a good indication of, this is a 21, so a line relay. This is B1, so I'm guessing it's a backup. And this is Schweitzer relay showing, your inputs, your outputs, your DC feed, and then what we're seeing a lot of is how we're going to wire it up, right? So we have our test switches, we have our interconnect points, we have our wiring points, our breaker points. So we're taking that one line and we're zooming in a little further on how we're going to connect all these DC inputs and outputs. Keys to a great DC schematic. So we follow the relay one line. We talked about that. The importance of the relay one line. We've gone over that quite a bit. There's a lot of high level info in that relay one line, and now we're honing in on the specifics on what inputs, outputs, what vendor info is shown, how we're going to connect it, make sure our polarities are correct, make sure our terminal points are correct. Again, zones of protection. As far as the DC schematic, that's what we're tripping. If you have a line relay, you want to make sure you're tripping the right breakers. You can certainly screw that up on a DC schematic, tripping the wrong breakers outside the wrong zone. So as simple as that may sound, it's easy to screw up for sure. Designed to be wired. There's a little typo there, but we want to design specifically like the lockout strings, and we'll talk about that in a minute, on making sure you're connecting spatially within the control house, the right contacts, the right trip chains, right? You want to make sure that you're not bouncing between cabinet 1 to cabinet 8 to cabinet 2 to cabinet 7. And then does this make sense, right? Is what we're designing make sense? Could you go out in the field and explain it? Ultimately, that's a lot of what we're doing here is making this constructible at this point. All right. So as an overview, relay systems universally use DC voltage for their controls. Common voltages are 125 volts. That's the most prevalent. 48 volts probably coming in close, a distant second, and then 250 is less and less frequent. We show the interconnection of components and how they function. So we show oftentimes you'll show even the cable number on the schematic. That's not uncommon. But you want to show basically how you're going to wire it, how you're going to interconnect it, and then additionally, you can show the cabling on a schematic. Allows user to trace control paths to the circuit. This is a big one, definitely when it gets to testing and commissioning. They use these schematics to ring out panels, and by ring out, take their multimeter and prove that your DC plus rail is intact, and then your same thing or your negative rail or your trip rail. So it's very, very much used when it comes to testing your mission. Specific terminal numbers and test switches. So, we talked about testing missioning, test the terminal numbers and test switches. This is going to be helpful for the electricians and the panel fab on how they wire this up, because they're looking at more of the point to point. And then their own QA QC, they will ring out the panels as well. Intermediate connections to terminal blocks. Sometimes they're shown, sometimes they're not. If they're not shown, what you'll see often is testing commission will draw them in, or sometimes design will put them in on a hidden layer as a kind of a favor. And that I've seen that done, not so much in the competitive bid world, but more in the EPC or ways to gain efficiency on the testing side. So again, PTE, that's testing and energization. Their use, again, functional checkout, troubleshooting. When we talk about schematics, we're talking mainly about the relay schematics, and a lot of those are dictated on the manufacturers. So this one, we're talking about GE, and the benefit to GE is it's fully modular, and you'll see that here where power supply goes here, CPU goes here, then typically it's your voltages, your 61850 process bus will go in this, and then the rest is reserved for IO, and the last one being inter-relay comms. So like your L90, this would be where your lasers or LED goes. So the nice thing is if you need more inputs instead of outputs, you could swap out a card, or if a card fails, you can swap one out. This is a very common relay used throughout the US. The downfall is the manual for this GE relay can be a little trickier. You kind of have to build. Sorry, it logged off. Let's see. I did download it. So that you kind of have to build it off of these little blocks here, and they do have more zoomed in versions. The Schweitzer relay is a little easier, where you see here, here's your CT, your VT inputs. So you can kind of piece it together this way. And it works fine. If we're looking at comm processor, here's where it's throughout the manual. It's in here, and you can look this way too. I prefer the Schweitzer. It's a little easier to read. If we're looking at a Schweitzer manual, they have the input outputs boards here. You can also download or develop your own configuration over here by selecting firmware, and then you can work your way through this. And at the end, it'll actually set you up with a PDF of the actual rear plane that you're looking for. But again, a lot of people prefer the Schweitzer as far as usability, if that's a word. Let's see if I can go back to the PowerPoint. But they both have their advantages and disadvantages. I'm not here to sell you on one or the other. They're both used prevalently throughout the US. Schweitzer does not have the modular function where you can pull out cards and insert cards like GE. Some models do, where you can replace, like I think the 411L, you can replace the lasers, and certainly in their Axiom model, which is more of an RTU, it's a modular setup. So indications, they both have these lights on the front showing their indications. You know, if you have a overcurrent trip, you know, a reclose, lockout, reset, sync, check, lockout relay. And these are all fully programmable, and you'll get into that a little later, I think. And then you also have these programmable push buttons as well that you can, at least on the Schweitzers, you can print off individual cards to put whatever label you want as far as the what function you have programmed here. Now that we've covered the Schweitzer and GE relays, you know, what do we use them for, particularly in the DC function side? One of the bigger attributes, one of the bigger functions that we use is breaker failure protection. And if you're not familiar with breaker failure protection, sorry, I have a cold. That's why I keep clearing my throat. But one of the bigger functions certainly is this breaker failure protection. What we're looking for is a protection scheme to isolate in case one of these high voltage circuit breakers fails. So we're looking at these breakers here. You hear stuck breaker protection. Most people use breaker fail. So typically what we see is a fault. Let's see if I can draw. So there'd be a fault here. This breaker would trip. Put a check there. This one wouldn't trip, right? So if that doesn't happen, what we're looking at is to clear this fault, because there's still current coming in from this side, we need to trip the breakers out this way if we were to extend this bus out. So how do we do that, right? And we'll cover that in a second. But you know, it's important to identify this condition. Otherwise, you're just dumping current right through this ground fault or phase-to-phase fault. So why is it needed? You know, here's some images of, I guess, a failed breaker. You know, it can cause excessive equipment damage, and you could start out with say a line to ground fault, say small, and then it could grow into a three-phase to ground fault with a much higher current current draw, and could result in additional equipment damage if it's not cleared quickly. Let's see, so breaker failure protection. So when we're looking here in this straight bus configuration, say this breaker fails, there's a fault out on the line. What we're looking at is this is feeding the fault, this is feeding the fault, this is feeding the fault, and now we have 3 times fault current. And say if there was a generator out here, that could contribute additional fault contributions here, but not through the bus or the breaker. But you know, what we're trying to do, at least locally, is to trip this, trip that, trip that. And then you could have a DTT scheme, a direct transfer trip scheme, that would trip a breaker out in the remote station to clear that out there. And that's what we're seeing here is we have a fail and we're tripping these breakers. Well, I guess that's all good theory, but how do we do it practically, right? So what are we looking at? You know, if I were to clear, I don't know how to clear this. Let's see, erase all. All right. So what we're looking at is, as far as a relay detect time, so we see a fault. No, this is normally operation here. Normal operation here. And then the fault occurs. So right here, we see say a line to ground fault. At that point, our 50 element, so this is our instantaneous overcurrent element. So this is probably say a three-phase fault. At that point, there's a little bit of time between detect and trip, right? There's always, nothing happens truly instantaneously. You're going to detect this in a few cycles, and then you're going to try and trip it within, you know, a couple cycles, 3 cycles, right? So this will probably happen within, say, 6 cycles. At that point, you're going to try and trip this breaker. At that point, your line will say BF, you'll do a BFI, breaker failure initiate. If it doesn't, if there's still current going through here, then after this time here, this 62 BF time delay, we still see fault current going through here. Then we're going to declare this a failed breaker. So right here, this is the preset time, still see fault current. Our breaker is just not opening. So at that point, we're going to trip this, and trip this, because that's the only way we're going to trip the fault at that point, right? We tried to trip it. Some utilities will actually try and re-trip it right about here. And if that doesn't go, then they enter into the rest of this time delay, and then they'll clear the bus. So let's clear. Let's see. You'll see. Just add a cycle on top of this. You can see. So this one's even. This is showing a cycle. So this is what, one cycle, 2 cycles. So it happens very quick. You don't want that fault resting on the system. Breaker failure. This is logically how it's shown. So yeah, this one has the 52 contact, and then the BFI going to a breaker failure scheme output. Typically, you'll see a current added to this. If it's just straight a 52 and a BFI, that's usually called a no current BFI breaker failure, which is used for situations where you don't have a ton of fault current on your system in that part of the system, but most of the time there's a current in that equation. So again, this is just showing different considerations when we're talking about how we're looking at the fault current. Fault starts. Here's where your BFI kicks in. So this is really where your relay acknowledges there's a fault, tries to trip. When it tries to trip, it also hits that BFI. Just saying, I'm trying to trip, let's start the timer. And then hopefully the timer doesn't get a chance to elapse before that breaker trips. If the timer goes the full length, you see here, if it interrupts here, this timer will just stop. No worries. Breaker tripped, we're good. If the breaker doesn't trip, the timer continues. You have a margin, and then you declare a breaker failure trip. And then you account for, this is your interrupt time for the backup breakers to trip, at which point the fault's cleared. And this is when we go back to the one lines, this is our n-1 consideration. And we're not trying to say we're looking for additional breakers to fail. This is really our contingency. So we have a local fault. Our contingency is one of the breakers fails, so we're going to trip our backup breakers. And that's pretty much where our protection stops. Types of conditions that will cause a circuit breaker to fail to open. Open connection in the trip circuit. So our trip circuit either has a issue or isn't wired properly. There's a short circuit of the trip coil. It's very possible blown fuse somewhere in the trip circuit. Failed trip coil, that's similar to the short circuit of trip coil. Or there could be a stuck contact, relay contact. Mechanical malfunction could happen, incomplete travel, so mechanism, or a pole disagreement where, say, some of our poles trip, but some of the others don't. Typical breaker failure scheme. All right, so this is one that we installed in Texas. And I guess what I want to show is just kind of the application, what we're looking at when we're doing our design. So we're looking at, for this breaker, for this line, right? So we have a fault. Say we have a fault here. What we'd expect is this breaker to trip and this breaker to trip. So if we were to assume this breaker would fail, what we're looking at is this line protection sees the fault, tries to trip this, tries to trip that. In addition, it also sends a BFI, a breaker failure initiate, to 1x8, 1x5. It sends that because it's saying, I tried to trip you, start your timer. So the logic will say, okay, the breaker's been, then, the breaker trip's been tried. Me as a relay, I'm going to start looking to see if it actually tripped. So at that point, you're going to start your timer and you're going to start looking at currents and the 52 contact. So what we see over here on the left, here's our BFI 1. We're looking, here's our line relays, right? Your 321, your 87L. So you got your primary, your backup. Either one of those sees the fault, it's going to try and trip it. You also have your transformer relays, also hitting that in the additional bay. Over here, your transformer relays are here. So if those see a fault, they're also going to BFI the same breaker, through BFI 1, 2, or sorry, BFI 2 or BFI 3. And usually you'll see just one input. This one, they do separate inputs. I think part of it is so that if there's not enough fault current in one of the nodes, they can do a no current BFI. And they have more flexibility on the settings that way. So as we saw in the timer, if we were to go back, say we trip, we try to trip, we BFI, timer runs out right over here, right? Timer runs out. At that point, what you're gonna do is, after the time delay, you're gonna close this contact. You're gonna trip a lockout. And breaker failures always trip lockouts, whether it's through logic, a logical latch, or a physical lockout. You always see a lockout. And what we see here is, on this side, this is the outputs of your lockout. So see S55, 1X, 1X5, that matches this. So this is how it's tripped. This is the output contacts of those. So what we see is we're locking out the closing of each of those breakers. So 1X2, 1X8. And if we go back, let's see. So we're locking out the closing of these breakers, and we're also tripping them through trip coil 1 and trip coil 2. The reason being, if you have a failed breaker, you don't want SCADA to have the ability to close these breakers remotely without someone going on site and doing a physical reset. So you see, you got TC1. They're not doing TC2. Some utilities do TC2 as well. Acknowledging that if the breakers failed, we're gonna trip the surrounding breakers regardless. So it doesn't matter if we're doing TC1 or TC2, but that's more of a preferential thing. And we also lock out the failed breaker as well, so no one tries to hit that again to try and close it, because there's just something wrong with it at that point. There's a lockout status that gets sent to SCADA, and then additionally, there's a DTT that gets sent. We talked about the line fault being the issue, but if we were to go back, say the transformer was the issue, right? And there's a fault here. Say there's a fault there, and this this breaker's stuck. At that point, the only way to clear this breaker would be to trip this one, which should have tripped successfully. This one failed. You're going to trip 1x8. So what you're looking at that point is, because this has failed, you're going to need to trip North Bennington out. out this way. So you're going to send a DTT through your carrier scheme or fiber, whatever medium you got. So when it comes to DC schematics, we spend a lot of time on breaker failure, whether it's in the closed scheme, the trip scheme, this takes up a lot of our time when it comes to DC schematics. So we talked about, I hinted at a power line carrier. We saw it right here. We have a wave trap, but basically a power line carrier that sends a wave, a frequency on the power line, which is used to help communicate some of our transfer tripping schemes. And to do that, we need a separate device. So we need a carrier unit. We need a carrier accessories on the CCVT, and we also need a wave trap. So what we do here, is you'll see, is we use outputs from our relays to start our carrier, and then there's a carrier stop as well. And there's different types. There's more to it than what we're showing here, but I guess in the interest of time, I'll skip on to the actual transfer trip, but just know that basically there's frequency shift keying, there's on-off carrier, and for the most part, these carrier schemes are going away, mostly due to the cost of fiber, particularly optical ground wire being cheaper. So less and less of these are being installed going forward. But if you do encounter one, they require a frequency study, and then working with the vendor to determine how to hook this up as far as the manuals go. All right. So transfer tripping, again, you can use the carrier equipment. Most of the time, you'll see it done over fiber, and by fiber, there's basically two types. There's a direct fiber and there's a multiplexed fiber. They both use fiber, but direct fiber is like a point-to-point communication versus a multiplex is more of a ring topology where you can send it one way or the other. And along those lines, an important aspect to look at when you're doing the transfer tripping. This is a little outside of the DC schematic realm, but what you want to look for is diverse paths, so that if you're sending a DTT, particularly on a bulk power system or a bulk electric system circuit, you want to make sure that your primary and backup, or your system 1, system 2, isn't utilizing the same fiber. And by that, I mean same path, I guess. So you don't want the DTT for your primary one and your backup to be on the same pole, the same fiber cable, the same trench. So that there's a lot to it other than just saying, oh, it'll get there. And then I guess as far as the schemes that go on the fiber, we talked about direct transfer trip. That's mostly used for breaker failure or a special protection scheme. In an instance, you want to trip the remote breaker. POTT, your protective overreaching transfer trip. I think that's been covered. If not, we can cover it later. But you also have a protective underreaching, your directional comparison blocking on your directional comparison unblocking. So all these schemes, I guess at a high level, their main goal is to help speed up the protection. So you're not relying on what you just see at your station. You're trying to utilize information at a remote station to come to a better decision on how to trip that line. And when it comes to DC schematics, we're trying to use our inputs to say, I see a fault, I don't see a fault, I have a stuck breaker, or a don't, right? And either way, you're either trying to direct transfer trip or to unblock the other um, the other end of the line. So this is showing our carrier scheme where you have your CCVT, you have your line tuner, your line trap. So this will be where you induce put a frequency on the line, and that could either shift. So you shift your frequency and indicate you see something, or you put a frequency on. So there's either on off or a shift key. So you either shift that frequency or you just turn it on or off. And what the line trap does is prevent that frequency from passing on down to station. Instead of station B, it could pass on to station C or D with a similar frequency, and it could accidentally cause a miss op. Another big part of what we do with DC schematics is enunciation and alarms. We have different indications as far as local remote, all the way to control house alarms, right? So we could have we should have control house fire alarm, control house high, low, and all those, they're not necessarily important in the system, but they could indicate a fire at a control house that could prevent your relays from operating, right? So beyond just the circuit switcher fail or your trip coil fail, you want to include HVAC. You want to include loss of DC, loss of AC, a ground fault, just for your DC system. So it takes a real holistic approach to these alarms, and sometimes they got to be grouped, or they want to be grouped. Maybe they don't want a transformer, LTC, oil, filter, high pressure. Maybe they just want that to be grouped in the transformer major. They don't want all these individual. I mean, you see here they only have so many windows on this. They probably don't at a larger station. They don't want every single transformer alarm to be individual. So, and when you're looking at enunciation, if you don't have an HMI, if you have an enunciator window like this, it's very important to make sure you have this grouped the way that SCADA and the field wants, so that when the field folks show up on site, they know where to go to help figure out where the fault is. All right. So this is just showing the inputs of the enunciator, how it's wired up. I guess the only thing I really want to point out here, other than sometimes the DC voltage of these is a little odd. So this one's showing the 24 volt DC, which happens, and at that point you need a power supply. Typically in most substations, so you need a power supply, and you need to make sure your enunciator feed is different from other DC, your 125 volt DC. But often it matches the rest of the station. And then here you see some grouping. Typically when you see wires go in and out like this, up and down, versus a more nodal approach. Let me grab my pen. So when you see a schematic go across, down, and up, that usually means that's exactly how it's wired. So here you see that. So if I were to see a schematic like this, I would think, all right, we're going to wire from B52 to A33 across to A42 to A39, which isn't the best way to wire this at all. You would, in this instance, you'd rather go from A33 to 39 over to 42. So I guess be cautious of using this unless the client specifies that. Typically, if the schematic is just more like this, then it doesn't matter how you wire it. But if it's up and down, if it goes in and out, that's usually a as wired type schematic versus this is just a node, right? So you could wire this however you want. You go 3C1 to 3K1 to 3D, whatever makes sense to you, right? But this indicates to me that I should wire it D4 to D12 to D20 to A27 to B52. So, but that's not always the case. But I would, if I saw the schematic, I would definitely ask the question. And this is showing, this is more of an older type annunciator and alarm circuit. This looks like a GE D20, D200 with each point using these little Phoenix type blocks. So one thing to be careful of is the size gauge wire you're putting on those. Usually these need to be a stranded wire 14 gauge, a 10 gauge solid probably isn't going to work with this type terminal block. So it's just another thing to look into, right? Any of these, when we prefer to go back, any of these relays, we kind of take for granted because they all accept 10 to 12 solid. But you shouldn't, because once you especially once you start getting the alarm and annunciation, it's not every wire will fit. These are pretty delicate connectors, and they're designed a lot for the industrial and facilities. But when it comes to utilities, we need to make sure we're using 18 gauge or 14 gauge wire and into these type terminals if you're utilizing this type of annunciation or RTU. FT switches. This is an important one. They are vital to what we're doing. They're used to isolate from both relays, potentials, also our DCs. All relays need to be tested before they're put into service, and these are very valuable on how to test them. And actually, there's if you were to go to a website, you can let me see if I can pull up the website. All right. So if we were to go into search, type in FT1 switch config, ABB has a really good configurator. It's been a minute since I've been in here. All right. So this is a really awesome configurator that helps you, if you want all potential. So this is just straight, isolation. So you pull that, it's isolated, right? Or you can do all current to current. So this has a shorting block if you just see here. So this blade will short here. So this would be used for 5 currents to help short it out, because you obviously don't want to open circuit a current. So that's what this is used for. And you can play around with this. You can change your handles to red if you want, and all this, if you hit configure, it pops out with a part number. Right, there's your style number, and then also you have front connected, so all your terminals are on the front here if you want that, or you can switch to your FT19R and do something similar. So you can pick different options here. So this is very helpful when you're doing designs and you want to see. You can search by code too. Apparently that was one of the last codes I looked at. So again, I use this when I'm doing design or checking just to make sure the part numbers line up. And every time I do a schematic or wiring diagram, I make sure that the part number actually lines up with what I see here. So the website, it used to be FT1 config, but now I guess it's spine.abb.com/ft switch/default. But I think if you just type ft1 config in search, you can get here eventually. All right, so back to this. So another isolation device is a PK block. The main difference is here you see you pull it down individually, which might not be ideal, especially with differential circuits. I guess high impedance differential in particular can be an issue, where you would isolate individual phases of the CT. So PK blocks, I've seen this mostly again on high impedance diff, where this block you would pull out and all at once you would short or open all the circuits connected to this block. So this just yanks right out. So and it's not easy to pull out. You have to intentionally pull it out. So I've seen it pulled out a couple times, and it takes a little heft. Oftentimes, I guess when you're designing, I've seen people spec this out so there's 2 blank plates behind it, because you have to drill this out and install it, because of the force that it takes to pull this out. So you'll see a double blank plate installed wherever there's a PK block, just for a little extra strength behind it. And again, the same function, just they're all disconnected at once. And this is typically made by GE. So reasons for having the isolation points, again, here's your reason. You can just open each of these points individually. You can test them. You can inject, or you can make each input go high based on your test set as you need, just to test out each individual circuit. All right, so that's test switches. Now we're going to move on to DC station service. So obviously we need DC to feed the whole system. And to do this, we need to do our own calculations. So we need to account for the worst case scenario. We need to size the battery bank correctly. We size the DC panel board correctly. And then circuit breaker size correctly. So let me hop over to some drawings. All right, so here's our DC system. So looking at each of the circuits. So this is a pretty big station. We have a lot of circuits, very few spares. So what we do is that for this client, they have a calc, and there's IEEE has their own calc, where you would put in each of these constant loads. So every relay is constantly pulling a DC load off the system, and then additionally, we will calculate the overall the momentary load. So in this case, I believe it was this node. So here we calculated based on a fault here, we would trip this breaker. So we'd have that trip coil, we'd have this trip coil, and then we'd have this trip coil, we have this trip coil. So these trip coils would be added to the calc. And then most of the time, occasionally, not this utility, but other utilities would say, okay, well, that trip failed, so we need to include this trip coil as well. So based on the momentary and the constant loads, it would spit out a battery size. And you can do this with, I think BAE, this manufacturer, they have a calculator as well, if you want to go to the website. So in this instance, it came with a 270 amp hour battery. So based on that, you want to make sure you specify the right main panel, so the right fuses, right amp fuses, I should say. Here we have a temporary battery connection. This is for any maintenance needed for the battery. The chargers need to be sized based on both the battery and the load, the continuous load. And then oftentimes there's 2 chargers or 2 batteries. So here we have 2 chargers. This is 1 battery. I'm not sure if there are 2 batteries on this one, but there are definitely 2 chargers. And then moving down, you want to make sure your DC panels are sized based on that continuous load. Likewise, you want to make sure these are specified properly based on the draw from, say, your circuit breaker. If you're drawing more than 30 amps, certainly that's a problem. If your voltage drop requires this to be, say, you can get by with a 12 gauge or a 14 gauge wire. You wouldn't want to put a 14 gauge wire here if you have a 30 amp main breaker, because what that does is your circuit's limited to the current draw of a 14 gauge wire, which is below that 30 amps. So you want to make sure your wire is also sized in according to that breaker. This isn't the most exciting stuff, so I apologize if you're currently sleeping, but it is important because you don't want this cable to be a fuse. And this is one of the more common mistakes I see from young engineers coming in. So hopefully you're paying attention right now, because that is a big one. Moving back to the presentation. We're almost towards the end. So here you see our primary, secondary batteries. Usually these are separated by rooms. This is a pretty rare configuration, honestly. I haven't seen too many where the primary and secondary are not separated by a room, a wall, or something similar. Same thing, separate panels. Usually you have the same main, but maybe separate downstream panels. And then separate chargers. And these are usually a little closer than they're close to where the batteries are. So they're usually separated more than 12 inches like they're shown now. AC station service, very similar as far as sizing, what I talked about, so I'm not going to repeat myself there. The big difference here is sizing the transformer and then where the source comes from. So I'll try and focus in on that. So the panel board locations, those are important. Sometimes they have some in the yard. They definitely have them in the control house, but the yard locations are often placed to help reduce voltage drop considerations. Verify station service, transformer connections. Are you connected Y, single phase? Are you connected open delta, broken delta? Are you connected on the tertiary of a transformer? Are you getting your feed from a distribution circuit outside the station? These are all options I've seen. Consider maintenance, make sure it's accessible, and then consider future expansion, both in the transformer and the panel sizing. So you should always use your client standards. That's kind of beat that drum enough, but consider worst case scenarios as far as what's going to run. Pay attention to protective relays that trip breakers using lockouts, and then make sure to use data sheets. I guess overall, another thing to consider when you're doing any of this is physical or design constraints. Looking at some of these, you see this panel is clearly loaded, where you have terminal block here. This is the standoff terminal block. So you have wires on top of wires. This is it's not ideal at all. So if you can avoid situations like this, and this is where site visits at kickoff can help alleviate some of this, where you can identify better places to install relays, protection, controls, and avoid trying to double up on terminal blocks. Same thing here. This is a station that I worked on where I had to turn sideways to walk down here. So this is not ideal when you're trying to install a new relay or do any design if you have to turn sideways to walk down there. So this station actually was getting demoed and a new one was getting installed. So that was lucky, but sometimes they try and reuse these as best they can to limit costs. So, and then this is just showing, make sure to consider physical access when it comes to testing. So when it comes to design to field communication, I consider what makes a good communicator, and how can we collaborate to avoid common errors. Showing this workflow, I guess it's pretty important. I didn't come up with a slide, but we can step through it. Typically, where the field gets involved is post IFC. So I'm usually involved to IFC. It gets kicked to construction testing. If there's any errors or corrections needed, comes back to me. We'll issue a design change notice, ideally, and that'll go back for corrections, and then we'll get the as-builts back. I will say an important part through all this is to communicate. If you're relying on emails only through this process, that's not good. You're gonna miss something throughout this. So if I get this email here, I'll probably call someone and be like, all right, what's going on? We designed it, we checked it, we were expecting X, Y, and Z. Why are you seeing this? And they probably have a good reason, right? And then we'll move forward with a better understanding, and come back with a good answer. Likewise, if we get as-builts back and they're showing they changed a bunch of stuff in the field, I'm not just gonna draft it and say, oh, all is good. I'll ask some questions. Why'd you change that? It doesn't make sense based on what we designed. And they probably have a good reason. If they don't, maybe you have a good reason for them not to have changed it. So, and then in the end, you can close out the project. So this is showing one-way arrows, but I think ideally you want this to be kind of a two-way path. I'll draw my arrows. Likewise here and here. So that's pretty much it for DC Schematics. Again, if you need to get in touch with me, you can reach out adam.benedict@PowerENG, and I guess that's the end of this presentation. So thanks for your time.